Good morning. Today I'm going to be competing in educational round 90. I'll be competing in the contest and like sharing my thoughts a little bit. And then after the contest I'll go over all the solutions. So hopefully it'll be fun. It's not rated for me because it's Div 2 only, or I guess rated for Div 2 only, but I'm still officially competing. And then for educational rounds, the scoring is ICPC style, which means like you're encouraged to solve problems faster because you get less penalty points if you do. But more problems is always strictly better than fewer problems, which I think makes sense. All right, good luck, have fun. Two rival donut shops. The first sells donuts at retail, $8. Second sells them in box. So a bunch costs $C. You want to buy X donuts, then you have to buy the smallest number of boxes such that the total number is greater than or equal to X. Okay. How many donuts can you buy so that they are strictly cheaper in the first shop than the second shop? How many donuts can you buy so they're strictly cheaper in the second shop than the first shop? What do they mean, how many can I buy? If any of these values, then they should be equal to -1. You can buy one donut is cheaper in the first shop? No? Am I wrong? Buying any number of donuts will be cheaper in the second shop. So they cost, oh, $C, I see. So if C is less than A, the answer is -1. Or what's the second number? Well, I don't understand the second number. Why is this 20? 10 for $4. How many donuts can you buy so they're strictly cheaper in the second shop than the first shop? Oh, if there are multiple answers, print any. Yeah, so it's always going to be either 4 or 1, right? So this could just be 1 or 4, I guess. Or just some gigantic number. Yeah. Okay, so this is very caseworky. So if C is less than A, then okay, so if C is less than A, then this out -1 space. I guess just buying 1 would be fine. You can buy B. Okay. Otherwise, if let's make these longs. If A times B less than C, well, okay, otherwise the first answer is going to be equal to 1, because if you buy 1, or wait, strictly cheaper, so this should be less than or equal to. What if B is 1 though? B is at least 2. Yeah, yeah, I think that should be fine. Okay, so if C is equal to A, then we can buy 1 of the first. Okay, so now in second answer, it's equal to A times B. If this is greater than C, if it's greater than C, that means we would prefer to buy B things, so B. Otherwise, if it's not, -1. Okay. I guess this can be a long. So first ants. Right. So I think that should be fine. 1, 10. 10 is fine. We can buy 10 of them. Then 1, -1. Okay, so in the second case, if you buy 1 donut, it is cheaper. I see. The third case, 1 and 2. That's what I print. -1, a very big number. Good. Okay, so I guess that took a while. It's hard to read. Ooh, game theory. All right, playing a game. We've got a binary string of length s. Binary string of length s. Binary string s. Sorry, consisting of zeros and ones. That's what binary strings are. They make alternating moves. In the first move, okay, yeah. Each turn, each player must choose 2 adjacent characters, different adjacent characters, and delete both of them. Yeah, you can delete. Okay, see. If a player can't make a move, they lose. Both players play optimally. You have to determine if Alice can win. Do moves even matter? Moves don't, or do moves matter? Yeah, I don't think moves matter at all. Because if you have a string that's even, if you have an even length string, no matter how the first person moves, it'll be deleted entirely. If you have an odd length string, it doesn't matter. Yeah. Okay. So we can use a stack here, and then for char C and A, returns equals 0. So if stk.peak last equals C equals 1, then stk.remove last returns plus plus. Else stk.add last C equals 1. This out turns mod2 equals 0. So if it is 0 turns, then Bob wins, right? Player who can't move first, yeah, can't make any move, they lose. So if it's even, that means, what do we print if it's Bob? If Alice can win, net. What do you mean? Oh. Well, this is a Boolean. Push false, push true, and then it should be 0. Okay. Push true, popped and popped. Wait a second. Does the string shrink? It does shrink. Oh, they have to be different. I thought they had to be the same. I see. Okay, so I just solved the wrong problem. What if they're different? So here Alice wins, here Alice loses because there are 2 moves. So 0, 1. I don't think it matters either. I think this might be right. I don't have a proof, but I'm like 60% sure it's right. I don't know though, because I spent all my time solving the wrong problem. So I'll prove that later. You've got a string of pluses and minuses. You need to perform some process with the string. The process can be described by the pseudocode. All right, so what happens here? So looks like you go forever. Current step equals init. OK equals true. One indices. Yeah, OK. So I is going to be the position in the string. Res is, I guess you increment it. OK. Now if this character is a plus, then increment cur. Otherwise, decrement cur. If cur is negative, OK equals false, and break out of this here. Oh, so this is pretty much break out of this outer loop. Calculate the value of res. So calculate how many times we iterate through this loop. If init gets bigger and bigger and bigger, yeah, if init keeps getting bigger, it seems like it would not terminate. Cur equals init. Then we're going to iterate from I equals 1 to the length of s. And either like add or subtract 1 to the current value. And now if it's negative, break. Otherwise, do they guarantee that it will end? Oh, I see. So this is if it never is negative. Yeah, okay. Makes sense. So let's do the sample. Negative, negative, plus negative. So initially we start at 0, then we look at just the first thing. And now, okay, so that's 1. Then the next step we start at 1. So we look at the first 2 and then break. So now this is plus 2. And now we're at 2 and we look at the first 4. So now it's plus 4. So the answer is 7. I see. So we just need the first time the sum hits every negative value. And then sum those up, and that's our answer. So I guess minus 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 might be another good thing. So we hit the first one, so that's plus 1. Then we hit the second one, and that is plus 2. Then we hit the third one, it's plus 3. Then I guess we hit the third one again. Yeah, I think that should be fine. This just passes through the first time. 1, 2, 3, 4, 5, 6, yeah. Okay, easy problem, I think. So we need to go through all the characters, and then if ynet I is plus, so now sum at I equals sum at I equals, let's see, Now we need the first time for each value, right? Or I guess yeah, okay. So now if C is less than 0, then first of at negative C equals max.min first of at negative C, or this index. So now we have the first time we hit each index. For I equals 1, true, I plus plus. So now, if first of at I equals integer.max value, then ans plus equals n and break. Otherwise we can ans plus equals first of at I plus 1, this index plus 1. Yep, and then just out the ans. So we just keep track of all of the new minimums, like the first time we hit them. 796, cool. Keep track of, oops, what did I do? Is this the right problem still? Yeah. All the times we hit a new minimum, and that will be like the things that get counted. All right, problem D. You're given an array of n integers. Indices of the array start from 0. You can reverse at most one subarray, one contiguous segment in the array. Recall that, yeah, we know what a subarray is. Your task is to reverse such subarrays such that the sum of elements on even positions is maximized. So if the length of the subarray is odd, that's never, you never actually change anything, right? If the length is odd, everything stays at their parity. So you want the length to be even, and if the length is even, then everything swaps parity. So you lose some continuous range, and then you get the odd ones at that range. So you lose the even ones at that range, you gain the odd ones. Do they like change something? What are they asking? You have to answer T test cases. Oh, but the sum is small. I see. So we want yeah, I guess there are just two ways of doing it. Well, it'd be nice if we're gonna have parity issues here, like with like +1, -1. But all right, so there are two cases. So either the first thing is even, if the first index is even, that means it's gonna be like it's negative then plus, then negative then plus. So we want the biggest. Are all these positive? Yeah. So then we want, for a given endpoint, we want the smallest start point. Or I guess we want the biggest previous cumulative sum. At most one, right? Yeah, okay, biggest previous cumulative sum. Because we subtract out that. No, we want the smallest previous one. Because we want this value, negative this, plus this. yeah, we want the smallest previous cumulative sum. Only starting at like the valid split points. Okay, so that's the first case. The second case is the other one. So in that case, the first thing you pick is odd. So then it's like you skip this one, but then the second one will be plus, then minus, then plus, then minus, and so on. And in that case, yeah, okay. Easy enough. Okay, so now we need, well, I guess we'll just do it in here. So long ans equals 0, or what do we need to print? Yeah, 0, okay. So, alright, so now for int I equals 0, I is less than n, I plus equals 2. So this is going to be a start at even index. And now long best prev, or what is it going to be? It's going to be the min prev. It's going to be equal to 0. And this is going to be the current cumulative sum. So cur minus equals 8i. This needs to be I plus 1 really. And now, or I guess this should be a at 0. Oh, this is the amount that we gain. Yeah. Okay. This is the base. Okay, so that's really the answer plus the base is what we need to print. This is just the sum of the even indices. So if we start at even, then we lose this. Now cur plus equals a at I plus 1. And now ans equals math.max ans or cur minus min previous equals math.min previous or current. Okay, now we need to start at odd. So start at 1. Yeah, okay. So now in this case, we want to add the first thing and subtract the next thing. And I think that's it. Do we have a good number of test cases? Guess let's just try it. Not even close. Well, I got 2 of them right. Alright, so this first one is really long. The second one is better to debug, I think. Alright, so we have this array. Let's make it one test case. 7. So the base will be 3, right? 1, 2, 3. And now if we swap these two, we get plus 2 more. Ah, yeah, here you go. In previous equals 0, cur equals 0. Looks good. 26, 5, 37, 5. Print writer doesn't hurt, I guess. E, geothermal's got E, so let's look at this. The sum of digits of all of the numbers this through K. Oh, of the next 10 numbers, I see. Equals N. It can be a big number. Yeah. It can be rather large. Okay, isn't always 10. I see. It's usually gonna be mostly 9s, right? So like, let's think about it for a bit. So for small numbers, you have 1, 2, 3, 4, I guess 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what about 10? 10 would be 19. Then 11 would be 29, etc., all the way up to 99. Now you need a sum of 19, so you get 199. Yeah. That's I don't know. I don't like digit problems. They're annoying. The government of Berlin decides to improve network coverage in its country. Berlin has a unique structure. The capital is the capital in the center. Berlin has unique structure. The capital in the center and n cities in a circle. There's no verb in this sentence. The capital in the center and n cities in a circle around the capital. Maybe are in a circle around the capital. The capital already has good network coverage, so the government ignores it. But the ith city contains this many households that require a connection. The government designs a plan to build n network stations between all pairs of neighboring cities while maintaining connections only for these cities. This network will provide a service only if this one and the next one it will provide service only for these two. So you have a bunch of numbers, and these are the capacities. And then you also have a bunch of stations. Can we only put one station at each position? Assign each household a network station, so this provides connection to most this many households. Oh, I see. So we have B stations, we have to assign them perfectly. Yes. So we ignore the nth city though, right? But the ith city contains... Oh, n cities in a circle. Wait, why is there even a capital in this problem at all? Alright, fine, whatever. So we have 2, 3, 4. So this one, and this one. Okay. Yeah, so this makes sense. So it's like a matching thing, kind of. Except we can't do matching. Well, I mean, the sum constraints have to work out at least, right? So if the sum constraints don't work out, then it's impossible for obvious reasons. What else? Well, if we've got 3 things, let's do more than 3. Let's do like 5. So we've got these 2, these 2, these 2, these 2, and then these 2. Feels kind of like circular gassing bunnies. Yeah, I think I'm gonna work on this. I think this one, like the concern I have is this K part. If you don't have this K part, it's just add 9s in the middle. But the thing with the K part is that like it can overflow in non-obvious ways. Like yeah, you might have issues with big numbers, right? Well, I guess not. I guess none of these do. Maybe a brute forcer might be helpful for that. Like what I'm worried about is like what if you're gonna have some value mod 9 that you can choose. Oh, I guess, well, hang on. If you can choose the value mod 10 with this leading digit, then why bother? Yeah. So that's the solution right there. Right? Surely. If you can, because you don't know what it's going to be, but you can choose what it is here with the first digit. So that's that problem. What do I do? What do I do? I think I'll just implement, so this is like easy but annoying to implement, but I guess I should probably just suck it up and do it. Yeah, okay, fine. So do I want to use big integers for this? I think so. Yeah, let's try it. So static int sum of integer I string res equals I dot to string c in res and plus equals c minus 0. Alright, so now we can just use big integers and find the sum of all of them. So now, cool. So this is int sum, or target sum. And then k is this next number. And then I guess we can do this. So static boolean try with digits. Int n digits. Okay, so 42 is impossible. That is interesting. I guess what are the first 7 numbers, maybe? Odd. Yeah. Okay. So this is the number of digits. We also need the target sum. We also need k. So let's also just have this naive for all numbers like that are realistically small. Target sum. Okay, so now big integer start equals big integer dot value of 0. Can we start with 0? Or can x be negative? Oh, not negative integer x. Okay, so 0. So while start dot compare to should be fine. 10 to the 4th. Max BF is less than 0. Then okay. So int real sum equals 0 for int I equals start I. It's less than or equal to k plus plus. Then what do we want to do here? Oh. Okay, so real sum plus equals sum of start, or I guess what is this? This is, yeah, start dot, well, start dot add big integer dot value of I. And now, if the real sum is equal to the target sum, then we can just print the print start and return true. Otherwise, start equals start dot add big integer dot 1, and otherwise return false. Now if we pass with a naive, if we can get the target sum for k, then we continue. Otherwise int n digits is going to be equal to at least, well, it's got at least 3 digits. N digits is less than, how many digits might it have? 100 maybe? N digits. It's got 100 digits, we should be fine. Okay. So if try with digits, N digits, target sum k, and continue the outer. Okay. If we can't ever do it, then print -1. So this should handle everything we need to. So now we just need to do this. So, yeah, okay. So we're picking k things. Int end equals k minus or 9 minus k. Yeah, so 4 int, well, int n sum equals 0, 4 int I equals n, I less than 10, I plus, n sum plus equals I. So now we have the sum of the last digits. So we're int real sum equals n sum plus 9 times the 9 times what? 9 times the number of digits minus 2, because we don't count the first one, we also don't count the last one. Now if real sum is greater than or equal to the target sum, then return false. Otherwise, the first digit will be what we're left, or what's left. So int first is going to be equal to target sum minus real sum. Okay, so now if first is greater than 9, then return false. Otherwise, it's from 1 to 9. I'm concerned here. We can add 1 to 9. Can we add 0? I guess 0 would be the previous thing. So this shouldn't be an issue, really. Yeah, that would just be 1 fewer digit. Okay. So now, this will return true. This out the first number, 4 int I equals 0, I less than n digits minus 2, I plus, this out the 9 here. Okay, so now we've printed a bunch of 9s, and now after that, this out the end number. Well, I guess this can be a print line. Okay, let's see if that's right. So, blah, blah, we get all these right. That is not right. That should be way too big, huh? 99, sum is 99, the value is 1. Well, this one's right, interestingly. This one's also right. Why is this one wrong? So what would the sum here be? 1, 2, 3, 4. So it would be 4 times 9. Oh, this needs to be, yeah, okay. We also need to multiply this by k plus 1. What? Does this need to be a long? No, that should be fine. What is going on? -1. So this should be 45. 4 times 9 is, well, 36 times 2. 36 times 2, 72. So 99 minus 72 is 27. Um, 27 minus 8, or minus 9 minus 8 is 10. Yeah, okay. So now this needs to, because this digit's not going to change, that's right. Ah, that's a problem. Yeah, this is going to be an issue. I don't know if the solution's right anymore then. Because the first digit gets counted a whole bunch. So if left for first mod k plus 1 is not equal to 0, then we're in trouble. And false, I guess. So I think I may have just like, yeah, this might be an issue. I don't like this anymore. Are there lots of wrong submits to this? There are. Yeah, I don't buy this. I don't buy my solution. So let's just generate some data real quick to check. So the max will just 23. Okay, and thenegen. Some, well, let's do 1,000 test cases, or, yeah, okay. So now, if, what are we gonna do here? Int n during sum equals 1, has to be at least 1, right? Yeah, 1 plus random. One plus the next int up to 150. Int k equals, so next int 10. Out some okay. Okay, so this is the, what's going on here? I said 100 test cases. Oh, we didn't print 2. Yeah, that's too big. How big can they get? I do 8 digits, right? So 8 times 9 is 72. So let's make this up to like 60. Or I guess we just need to cut this down, huh? Yeah, that should fix it. 3, 4, 5, 6. What's wrong with that? Oh, okay, fine. It's just taking a while. This brute force is not working as well as I would have liked it to. Man, I wish I could switch. Okay, this will just be enough. Here's our input. Yeah, test case 6 I get wrong. So I say this is impossible. Wait, what? Oh, sum is 132. And the answer is that. Yeah, this is an issue. So my solution just isn't right. I don't know. Yeah, F might be interesting use of time, at least. Well, now I'm thinking about this. I want to know why, or like how you'd go about doing it. Maybe it's a DP. If it is a DP, it sounds like an annoying one. An annoying digit descent DP. All right, so let's take a pause on that. Work on the circular one for now. Got a bunch of things in a circle. How do we do it? Or not how do we do it, can we do it, I guess. If we've placed one of them already, then greedy works. And we can greedily place the smallest one that we need to. Is that true? Is that true? Maybe it's not. If we've placed this one already. Yeah, that's not true. You don't just need to satisfy this house or this this city. You need to Make sure you don't make the next one impossible. So when would it be? Well, oh, are they already given to us? Can we rearrange them? Wait a second. Wait a second. Dude, I'm just misunderstanding all these problems. They're fixed. The locations are fixed. Is that true? In the second case, oh, they're fixed. Dude, I'm an idiot. Okay, so that just means this is just like a Hall's marriage theorem problem. So is there some range where the sum doesn't work? That's all we're testing. Okay, I can do this. So we need to check the entire circle. I thought you could put these in whatever order you felt like. Let me just triple check to make sure that's not the case. Wait, check the designs. Yeah, is it? Wait. No, it's not. That's not the case. Is it possible to assign each household a network station? What is a network station? Well, what is a household? The ith station. Maybe this will answer our question. Maybe we could do this if we could rearrange them. In the fourth case, the fourth city needs 5 connections, but these two only have 4 total. Yeah, okay. So they're fixed. Okay. I thought you could like shuffle the second array, in which case the problem I think gets much harder. If you can't shuffle the second array, you just need to check all the pairs. So then this is an easy problem. So you need to check the entire circle, and then we need to find some way of like optimizing these checks so we don't have to do n squared of them. So we just have a bunch of positions, and then we have well, we need to check all the ranges. So what's this? We want get a bunch of positions and a bunch of these things. So we want to know what's the biggest prefix of like as we add another pair, or as we add another person, we add the thing to its right. So initially we start with just the bottom one, and then we add these two, or we add these two, or we add these two, or we add these two, etc. So we're going to brute force which station the important range is at, and then we want to say for all stations after it, we care about the cumulative sums. So we want the, what do we want? We want the minimum value of any suffix in a given range. So we could do an armq and cumulative sum stuff, I guess. Yeah, let's do that. Man, I can't believe I misread that problem for so long. Okay, well then the real question is, that's digit dp later. How are we going to do that? And log n RMQ should be fine because we just build it once. So what do we need? We need we want minimum. Yeah, we want range minimum, so this is fine. Do these need to be longs? Probably need to be longs, yeah. This is a long array, it's a long array. Long, long. Oops. Okay, so we've got our RMQ. Good. That's fine. So now n equals this. Okay, so let's do this ourselves. Iterate a equals int n plus n. So now we've read these two arrays in at like this maximal sum, or at this this range or whatever. So now int a sum equals 0. I guess these need to be long, so long a sum. Well, yeah, we just care about the differences really. Just at high, yeah, okay. So if there is a negative sum in total, then print null. Otherwise, it's plausible that we could match everyone. So now what we need is we need the cumulative sum array. So now we have the cumulative sums for our differences. So now we need an RMQ for those. Okay, so this is the diff CS array. All right, so now we've got this RMQ. So now we want to brute force the left endpoint. For int L equals 0, less than n, L plus plus. You could also save a log factor with min q if you needed to here, but I think this is easier conceptually for me. So int or long cs to sub is going to be equal to diff cs at l. Long far cs is going to be equal to armq.query from l plus 1 to so we want, well, I suppose this isn't entirely accurate. This is going to be L plus 1, right? So if we keep this, then we don't include this difference at all. So it's going to be L plus 1. So this will be from L plus 2. Or could it be empty? Well, it being empty won't be helpful. Is n at least 1? N's at least 2 even, okay. To n, or L plus n. So this will not include myself. Yeah, that doesn't include the far version of myself. Does this need to be L plus 1 plus n though? So if it's 4, 0, 1, 2, 3, 4, 5, 6, 7. So 3, we want to include 4 to 6. No, we want to include 5 to 7. Yeah. So L plus 2 up to 3 plus 4, yeah, so I think that's fine. So now long range sum equals far cs minus cs to sub. Okay, so now if range sum is less than negative b at l, this out no and continue. Otherwise, this out yes, I think. So, well, this is darn it. Oh, this should be if it's greater than b at l. Really? If the range sum so the far thing minus cs to sub will give me the range sum of all of the things after me, all of the top minus bottom. So now if the number of things at the top is less than, is greater than, yeah, this is the number of uncounted things. If this number of things is bigger than how many things are in the bottom, then it's not possible. That's RAID. Why is that not RAID? That should be fine. Clearly I'm doing something wrong. Okay, so or this isn't helpful, I guess. Far CS. I just care about the range sum. Oh, it should be. This is positive. Print yes. Okay. Print no. Okay, so then what is going on here? We've got yeah, all right, so I see my issue here. This shouldn't be this. This should be, no, it should be this. So what is the case we're getting wrong? This one here. So they say this 5 corresponds to these two. So at index 0, 1, 2, at L equals 2, range sum equals -2. It should be able to be -3. So at L equals 2, 2 sub equals -3. So these repeat like they're supposed to. The difference is cumulative sum, 0, -1. Yeah, okay, that's fine. We might want the maximum, actually. Yeah, we want the maximum minus the minimum. This thing right here. This is 5. So this is what this is. The difference here is 3. There's a difference of 3 right here. Yeah. So this needs to be a max Q. So we want the max Q. So if the max sum is bigger than this, then we're good. Yeah, yes, yes, no, yes, yes, okay. MLE? Haha. That's hilarious. MLE, really? Well, what was my time? Well, hang on. Oh my goodness. If I AC because of my low memory RMQ, Oh, now I gotta fix this though. Darn. So this needs to be math dot max of these two. That max edge query should be that thing. Okay. I think that's fine. Oh, now we gotta worry about this. So well, this is less than or equal to, I think. I think that's it. Resolved compilation problems. The other option is I can just invert everything going in. It needs to be long arrays. Oh wait. Yeah, okay. Not even close. Well, let's just try the other way then, because that's pretty easy. A equals int array a fake, except it's going to be a long array. Okay, so long. These are all longs. And then just make this a negative. I should probably be using print writer. Yeah, that's unfortunate. If I TLE, I don't know what to do. Oh, just wrong. That is unfortunate. That's pretty annoying. So why could it be wrong? Or should I move on to other problems? Yeah, looks like this is definitely the easier of the two. Okay. Well, why would this be wrong? It's certainly close at least, right? So this should be the same thing, just lower memory. Should be well tested. Yeah. The difference is this A minus this B. And I find the sum of differences. If that sum is positive, there are more people that need electricity than there are electricity stations. It's impossible. Otherwise, I get the prefix sums for every prefix. And I build an RMQ off that. This is a max query. And now this is what I'm going to subtract, so the stuff after me. And then the far CS, what's this? This is, well, I guess we could try rotating this by one. That would be a good test case. So now this is what I'm going to subtract, so this suffix, and then query from everything from this to the end. Find the biggest prefix sum. So the biggest prefix sum minus my prefix sum. If that is bigger than this, then we have a break case. This should be right. Am I out of time? No, another half hour. Gotta use the little memory RMQ, huh? Yeah, there's no chance this is wrong. So it's well, what would the issue be then? It's fine. Hmm. Am I doing this right? Well, would I even pass this case? Probably not, if I were doing it wrong. Yeah. Why is this not the case? I don't know. I don't know why I'm wrong. So maybe let's go back to this. Okay, so so it's pretty clear that what was my break case for this? It was case 7, whatever that was. Yeah. So the correct answer to this is not -1. The correct answer is this number here. So we can try all possibilities, I guess. So I guess dp at digit and then number of things, and I guess the target sum might even be valid. Equals whether it's possible. So yeah, I think that's it, unfortunately. Okay, so what are our choices? Well, if these are all going to be small numbers, that's fine. So what do we do if we can keep all of them in our range? We might also need to know whether we're bounded, like whether it's got to be we can, yeah, so it might be upper bounded or it might be lower bounded as well. So we can like cross the border in a bunch of ways. Alternatively, instead of crossing the border, we could distribute it to any one of our kids. So int min number. Well, okay, int digit, I guess. Which digit am I in? Int number of things, okay. And then int target sum. Returns whether this is possible. Alright, so how do we do this? If digits equal to 0, then there are a bunch of different things we can return. For and start 0, start is less than. We had to build back too. Ugh, this is disgusting. Yeah, maybe the build back won't be too bad. Alright, so for and start equals 0, start is less than what? Plus 10, plus plus. Or divided 0 is less than k, plus plus. This is really start plus k. So equal to k. And sum 0, sum plus equals start plus I. If sum equals target sum, then return true. Otherwise, return false. Otherwise, we've tried all of the one-digit things, so return false. Okay, so that's what we do if there's the base case. Otherwise, we always build off of one fewer digit. Well, we can do this too. So if target sum less than 0, return false. So now, there are a bunch of things we could try placing. And sum left will be the target sum minus whatever we place times the number of times this will happen. Okay. So now nothing works, return false. Okay, so we have we've got this sum left. dt of digit minus 1, same k, sum left. So if this is the case, then return true. And that just means we're placing some stuff. We end at some other thing. Okay. It's also possible for us to overlap as well. What does that look like? So this means we place a bunch of 9s, and some other stuff. For int first thing is going to be equal to 0. First thing will be less than 9 or less than 10. First thing plus plus. Okay. And then what we're going to do, so now we need to calculate the sum left, or the sum used. Oh, we also, yeah, this needs to be in here, I guess. This can't happen if 2 place not equal to 9. If 2 place is equal to 9, then this would overflow. Okay. So, what is this going to look like? We're going to place whatever number we start with, and then a bunch of 9s, and then we overflow a bit. What number do we start with? Start with 2 place. Okay, so int small times be equal to, okay, what's the first going to be equal to? Well, if it needs to overflow, then it'll be 9 minus, or 10 minus k. Yeah, because we add up to k. Yeah. Okay. So this means it'll overflow. So int unadded first will be equal to 10 minus first. That's how many times this happens, times 2 place. After added first is going to be equal to k plus first minus 10 times 2 place. So if the first is 9, then it would be 9 minus 10 plus k. Yeah. Okay. So sum left will be equal to the target sum minus the unadded first minus the after added first. Now this has to be handled by the 9s and by the last digit. So for int I equals 0, I is less than k, I plus plus. Oh, we can just do this, I guess. So if first plus I is less than 10, sum equals 0. Okay, then sum plus equals 2 place plus 9 times digit minus 1, because it's 0 indexed, and we lose the first digit, plus whatever the last digit is, right? Plus first plus I. Otherwise, sum plus equals 2 place plus 1, because it's overflowed, plus a bunch of zeros which don't count, plus first plus I minus 10. Now if sum is equal to target sum, then return true. So now I should handle the cases where we can actually solve it. Oh. Okay, so how many digits do we want? Maybe, I don't know, 200? K will be up to 10, target sum will be up to 151. Okay, if dp add digit k target sum is not equal to -1, return dp at this thing. It's equal to 1. In this case, it equals 1. In this case, it also equals 1. In this case, equals 1. Equals 0. Okay, so what do we actually read in here? In target sum. Okay. So if dp at digit 0, okay, target sum. No, digit's not 0. Digit will be like 199. If this is the case, then print possible, else print -1. Never possible, huh? Yeah, of course. Digit equals 0. Right x out of bounds -1. Digit equals 0, we should always return, no? So how does digit get small? Digits equal to 0. Otherwise, call it with digit -1. Okay, it's possible. Digit equals 1. Well, clearly it's going to be -1, but why would it be, how is it -1? It shouldn't be negative, what? Oh, duh. Possible. Yeah. Possible, 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 impossible, rightly so. Possible, claims this is impossible. sum is 99. Times 2 place times this should be k plus 1. Okay, so we get it right now. Okay, we get this right, so now we just have to build back. Which we should be able to do pretty easily. Yeah. Okay, so if the sum is equal to the target sum, then sys out start and return. In this case, throw null. Case throw null. Skip that part. And then here we should be throwing null. Right. So two more cases left. What happens here? So here we just place some number. Yes, so boolean new placed equals new place is not equal to 0 or placed. Okay, now in this case we want to build back digit -1. Okay, some left, and what number? Yeah, this new place. Cool. And then we want to return. Okay, now this is the last case. So yeah. If new place, then sys out what do we want to print? We want to print the thing we placed. Okay. Otherwise, we're here. So yeah, so now if this wound up working out, then we want to actually print it. So make this new thing here. Okay, so if new placed, then do the same thing, print out this first digit. Okay, otherwise for int I equals 0, I is less than the number of digits, -1, I plus plus, this out a 9. And then the last digit will be the first number, right? Or that is the first number, hold up. First, wait, what is this? So oh yeah, print out to place. Now we print out first, always. Okay. So if this is the case, Build the back. 199. Okay. Target sum. Haven't placed anything yet. Oh, it's wrong. Null pointer exception. Oh, yeah. Should be 4. That's an odd bug to have, I think. -1. They're all right except this is a 4? How is this a 4? How does that happen? What? The first 7 numbers? So what is this going to be? Okay, how much time do I have? Good amount. So it's going to be 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. It is in fact 49. Wait, what? 42. One, 2, 3, 4, 5, 6, 7. Oh, this is 1. Yeah, okay. 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 1 plus 2 is 42. Okay. What number is this going to be? This is just this, or just this one? Man, thank goodness for these samples. Yes, a sample on F would have been great. First is 3. Target sum is 42. Okay, so if first plus I is less than, oh, this should be less than or equal to, yeah. Okay. One, or, yeah. Okay, fine.
Wrong answer test research.
Really? Maybe I need more digits? I am returning every time I print something, right? Build back. Oh, wait. Darn it. So this needs to be less than or equal to k as well. What was this? Wait, what was it doing? So less than or equal to k. So why is my f wrong? Ugh, that was a bad contest. Yeah, I don't know. I don't know why my f is wrong. Let's read G, I guess. Well, I don't know. I don't have time for G. So I can explain A through F. Yeah, I'll explain A through F and then do G on my own time. Figure out what's wrong with F after contest. Okay. So let's go over solutions. Easiest to hardest, as usual. We'll start with problem A. So you've got some donut shops, and there are a couple cases that, well, basically what you want to figure out is what number of donuts are each shop better than the other one for. So like if you want to buy this number of donuts, you should go to this shop. And there are other cases where some donut shops are just totally worthless because they're way too expensive. So you're given this A, B, and C. And so if A is bigger than C, so you can buy one for $8, or you can buy B for C dollars. Those are your two choices. So if it costs more to buy one than it does to buy B, then this is useless. So in this case, the answer can just be like, then A is useless. And if it's equal to C, that's useless as well, because there's no reason to go to it. You might as well just go to C. And then you can just print just like -1 comma B. So then you can do... if that's not the case, then it's possible that, like, if you want to buy just one donut, then you would want to buy it from A. So otherwise you can buy one from A. And then the question is it ever useful to buy something from C? And the answer is it is, only if buying B things from C is a good deal. So if you want to buy more than B things, either it's some multiple of B, in which case it doesn't really change because you're just multiplying it by a constant, or if it's not some multiple of B, then like you could buy fewer things of A, and that would give you a better deal for going to shop B. So that just, it's like a good exchange argument, shows that the greedy is right. So that's why my solution to A is I'm pretty confident for. Yeah, so this problem was interesting. I misread it in the beginning, but that's fine. So you're given some binary string for problem B, and maybe it looks like 1 1 0 1 0 0 0 1 1. And on a given turn, what you can do is you can remove two different things from the array. And maybe you remove those two, maybe you remove these two next, and then now you have these two things that are different, so maybe you remove both of them. And it turns out, and then you want to count like who wins, Alice or Bob. If Alice wants there to be an odd number of moves in the game, and Bob wants there to be an even number of moves. So it turns out that like whatever move you do doesn't actually matter too much. And I guess like you can kind of case it out. That would be one way of doing it. So if you have like 0, 0, 1, 0, if this is like the center part that you remove.
Always a pleasure hearing you,
Oh.
sir.
We have company 0. If
Understood, sir.
if you remove these two like this, then like it's still, you have nothing around you, and that would be the same as if you removed, if instead of like removing those two you remove these two, you're still left with 2 zeros. So I guess that's the case. What if you have like a 1 like this? Well, here you only have this choice, but after you remove it, it doesn't change. I guess if you have a 1 and a 0 here as well, then here you have this pair that you can remove. And alternatively, if you remove these two, you still have this other pair you can remove. So you can go through and show that like it doesn't actually matter what choice you make. Like the players, technically they have a choice, but really any move they make is as good as any other move. So you just have to count how many moves could you make if you do any strategy. And one strategy for that would be if you've got like some binary number. What you can do is you can just say, okay, well, look at the first one, now look at the second one. Okay, so you've got this stack of elements, you've got just the one in the stack, and since these two are different, you remove both of them. Then you keep going through. Here you have two different things again, so you remove both of them. Here you're going through. Okay, now you see this 0, top thing in your stack is a 1. Now you see this 0 again, top thing is a 1. So in total, I removed 1, 2, 3, 4 pairs of elements, which means there were 4 moves. And since there are 4 moves, that means what Bob wins, I guess. So yeah, so that's how you do B. Cool. Let's go to problem C, pluses and minuses. So this took me a while to read. It was like kind of hard to understand, but basically what all the problem is asking is you're going to go through this string and you've got some counter. So initially your counter starts at 0, and then it'll be 1 here, 0 here, -1, -2, -1, and then -2. So it's a lot like a bracket sequence if you consider this an open and this a close. It's like what the counter, what the size of the stack is at that bracket sequence. And now you want to know, like what you're going to do is you're going to add up things until it hits -1, and then you're going to add up things until this counter hits -2, and then add up things until the counter hits -3. Or if it never hits -3, then it's just the total length of the string. So all you need to do is you need to keep track of the first -1, the first -2, and the first -3. But there isn't any, so it's just infinity. So you just keep track of the first time your counter will hit each number, and then after you have the first time your counter hits each number, you just add up those indices +1, and then that's it. Solution to the problem. Cool. So that's problem C. You can also, like I did it in order in memory, but you can also just do it with a single sweep through the array, even. Problem D. This was a cool problem. I like this problem. So you have you've got some array of integers, as usual, and maybe your array is like 1, 0. It's kind of boring. I guess I kind of like the sample they gave. This is a good sample, I think. So what you're going to do is you're going to pick some array and you're going to reverse it. So you turn it from 1, 2. This one you would turn to 1, 2. Instead you could choose, maybe you could choose this array of like 3, then you get the same thing because this is a palindrome. But if you had, like, let's make it not a palindrome, so let's make it a 4 here, then the 4 would go to this position. So what your goal is for the positions in even indices starting at 0, you want to maximize the sum. The key observation, or one of the key observations at least, is if you've got some array here and you pick any subarray that's odd length, then the parity of each index doesn't actually change. So here this is like initially at an odd, so it's like 0, 1, 0, 1. This is the parity of the positions. So initially this starts at an odd position and it goes to another odd position. And this starts at an even position and it stays there. So that'll happen whenever the length that you choose is odd. So that's like something to avoid, because then your move doesn't actually work. And you could just make 0 moves instead, so that'd be easier. So now you know the parity is going to be even. And if the length of the range you choose to flip is even, that means all of these just switch spots. So if everything switches spots, you just have to know, okay, if everything does switch spots, what does this end up looking like? And let's draw out an array where things switch spots, so we can see what happens there. So we're gonna have some array, and initially what we'll have is we'll have this here, this number here, this number here, this number here, and this number here. And then we're going to pick some even length array. Maybe we pick an even length array that looks like this. If we do this, what happens is we get this number, and we also get this number, but we lose this number and we lose this number. So the difference between choosing this array and choosing nothing would be negative this, positive this, negative this, and positive this. So basically what we want is we can keep like a prefix sum that's of this form, like minus, plus, minus, plus, minus, plus. And if we're going to have this as our endpoint, the value is going to be, like, let's say this is like position A here. I guess let's call this position A because it's like before the range. This is position B. So what the value is going to be is it's going to be prefix at A or prefix at B. So we want this entire blue prefix. Then we want to subtract out this prefix. So it'll be this minus this, and that'll give us what we want left over. So prefix at B minus prefix at A. And we want this to be as big as possible because we want the difference between if we just didn't take any moves, like we want to improve what our score would be by as much as possible. That's the goal. So we want this to be as small as possible because we're subtracting it. So we just have to keep track of, for all possible A splits, what is the minimum possible thing it could be. And then when we get to each position, we're like, okay, well, if we're going to end our range at this position, then we want the minimum possible starting split if we end here. And we can keep track of that and take steps by 2. So that'll handle this case. There's one other case, which is pretty much the same, but you just have to remember to take care of it. This is if our range starts at a plus. It's possible our range starts at an odd index. So that might look like this here. And it ends at an even index. And if this is the case, then we have to, I guess, handle it slightly differently. So now our split points look like this. And if we have something like this, then we, I guess we have a little bit slightly different problem. We just have a different array to work with. And then we want the maximum subarray sum here as well. So yeah, I guess it reduces to maximum subarray sum, if you're familiar with that problem. There are easier ways of doing it than what I talked about, I guess. You can, well, I don't know. I guess what I talked about is easy enough. So yeah, so that's problem C. Or problem D, I guess, rather. Problem D. I thought it was a good problem. I liked it. Problem E, I thought was a terrible problem. Part of it was because I struggled on it and I went for a greedy when the answer was just a DP. But anyway, the idea is you're going to take some number. So you're going to like pick some number X, and then you get to pick that number. And then you want to count the sum of the digits in X, and then also the sum of the digits in X plus 1, and then also the sum of the digits in all numbers up to X plus K. And you want to say what's the smallest number X, where this sum is going to be equal to like some sum that they give you. So they'll give you the sum, and then you want to find the smallest number X where it's true. So there are a lot of things you might think, and as far as I know, they're not correct. One of those things that you might think would be some question mark followed by a bunch of 9s, followed by like some other number that you might not know. this is not the case. I have a break case for that. I guess that's really the only thing you might think. That's what I thought. Or I thought the other case would be it would be like some small number. But as far as I know, that's not true. So what you can do instead is you can do a DP. So it's like a digit descent DP. So what you're going to do is you're going to store a DP where your state is how many digits are left. And then I guess what this k is, right? So how many numbers you're going to pick. And then also what the target sum is. And then you want to store whether this is possible. So there are a couple decisions you can make. The first decision is you can place any one of the digits, or 0 through 9, not 0 through k. And if you place if you place one of these numbers, your target sum will decrease by the number you placed times k, because you're going to place that many of that number. Of course, if it's on the last digit, you just check all of the last possible digits, and then you check what their sum would be. One thing to make sure that you don't let happen is this is assuming that it doesn't overflow. So it's assuming all of the previous digits are fixed for all k things that we place. And that's important because here what we're going to do is we're going to subtract out like k, well really k plus 1 times the digit we place. And this isn't necessarily true if we overflow, and then like, so if we've got like 9, 9, 9, and then we don't know what this is here. If this is going to be like 7, and then 7 plus 1, and then like an 8, and then a 9, and then a 10, if this last digit will be like a 10, then when this last digit becomes a 10, instead of these being 9s, they're all 0s. So we've counted them as if we're placing 9, 9, 9, 10, but really what's happening is this thing out here becomes a 1, and then we're placing like 0, 9, 9, 9 for some cases, and then we're placing 1, 0, 0, 0 for other cases, and that's not a very predictable thing, so it's not good to let that happen. Instead, what I did at least is I said if you go into this DP state, you know that all of the previous digits, that you have to make sure they stay fixed. Which means for this last sum, you can't make the last digit, or for the last digit, you can't make it overflow 9 in some of the k positions. Okay, so what else do I need to cover? Yeah, there's one other case. The one other case is this one. It is possible you do want the digits to overflow. So if the digits are going to overflow, what will happen is you're going to place some number, maybe you place like a 3 here, and then you'll place a bunch of 9s, and then you'll place like a 6, and then you'll place like 6, 7, 8, 9, and then like this will turn to like 4 with a bunch of zeros, and then a 0 at the end, and then a 1 at the end, etc. So what you can do is you can try all of these, because there are only 10 different things, 10 different ways this can happen. And then for each of them, you can count each of the 10 starting points of the lastmost digit. And there are only 10 different things the lastmost digit can start on. So you have this. I don't think you need this many digits. I submitted with like 2,000 because I wasn't sure. But I think you probably need like 150 or something maybe. Probably not that many. The k, how big can k get? K is 10. This target sum is 150. And then this, you've got to order 100 transition. So it's, what, 10 to the 7th, I guess? But you can optimize it probably if you need to. So yeah, that's problem E. Problem F, I swear I know how to do. I don't know why I'm wrong, but I'll explain what I'm trying to do at least. And I think that might be helpful to some people. So my understanding of the problem, which isn't necessarily correct, is that you have a bunch of like people at each house. So you've got a bunch of these numbers. We've got like 2, 5. This was a good sample here. 2, 3, 4, 5. And then on the bottom you have these like bandwidth amounts, which are 3, 7, 2, 2. And this, like, they match up like this. and then this matches to this, and also matches to the 5 or to the 2 here. So each of these people has 2 places they can be associated with, and then you're gonna have to assign these in some optimal way. So if you wanted to, you could do this with flow, like in theory, if bounds were tiny, because you have a bunch of different people, and you can have like a massive number here. You can have like 10 to the 16 or something, and then you also have a bunch of different different networks, and you have again like 10 to the 16, or maybe not 10 to the 16, maybe it's like 10 to the 14, but still some big number that you can't actually run flow with. And then you have a bunch of these edges, and each network will be able to connect to 2 houses. And similarly, each house will be able to connect to 2 networks, or 2 different types of networks. Yeah, let's try this again. So this is the houses. These are the networks. Let's say these are the networks. And then these are the houses. And each house, okay, not 2, but 2 different types. So maybe this is like all one position, and this is all another position. So each house will be able to connect to 2 different positions of networks, but it might be a bunch of different networks. So you could run that with flow, and that would give you the right answer. So maybe that's what I should have done. Instead of trying to solve E, I should have just written out the flow, find a break case. But you can do better, and the way to do better is you can use this thing called Hall's marriage theorem, I think. And what that says is if you're looking for a perfect matching, the only way you won't find a perfect matching is if there's some subset of either the left half or the right half where it's obviously impossible. And obviously impossible is a informal way of saying it doesn't meet this obvious condition that like clearly needs to be true. And like the important part of this is that if there isn't any place where it's obviously impossible, then it's definitely going to be possible. So what is this obvious? What does obvious mean in this case? So basically what it means is if you have a bunch of nodes on either one side or on the other side, if you want a perfect matching, that means if you pick some of these groups on this side, if the total number of things these things can reach is less than the size of this group, that means it's not going to be possible. So for instance, like a good way of thinking about bipartite graphs, in my opinion, is like you have a bunch of men and a bunch of women, and then you have a bunch of edges which represent this male would be happy marrying this female. So here you've got these 2 women, and among these 2 women, they're only happy marrying a total of 1 man. And that means they can't both marry the same man, so this like is not solvable. But the important case is if for every set there's no break case for that. There's no version where like, okay, you can pick 3 women and among them they're only happy with 2 different men. If that's never the case, that means that you can find a perfect matching. So how do we check all of those candidate spots here? Well, you can notice in this case the only things that are like, okay, so what do the matchings look like? Well, if you have here all of your people, I guess, and here are all of your houses. So if you pick some house, that will introduce these people and these people. Or let's do people instead. You pick this person, that will introduce this like Wi-Fi router and this Wi-Fi router. And then if you pick this person here, that'll introduce this Wi-Fi router and this Wi-Fi router. So the important thing to notice, like the greedy observation here, is that if we pick this and we also pick this, then we've introduced this free one. So we might as well pick a continuous range. Because if we can pick a continuous range, that means we have some continuous range here, plus this extra one here. And if this person's going to be in any group at all, then we definitely want this guy as well. So now here's the observation. All we have to do now, like we've simplified this problem quite a bit, and what we have to do is we just have to check, are there any instances in which the sum of these things is bigger than the sum of these? That's all we have to check. And if there are no instances in which that's the case, then because of this Hall's marriage theorem that we talked about earlier, then it'll be solvable. So here is where I think it should be a pretty easy problem, but I wasn't able to get AC in contest, so I don't know why. I'll talk about, or I'll work on it after the fact. But what we can do is I think we can just double the length of each array. And we can brute force what this point here is going to be. So let's say we want it to be this point here. Then we can include up to 4 things on the top and up to 4 things on the bottom. So we can include these 4 here. And of these 4, what we want to know is for what prefix is the sum of like top minus bottom. For what prefix is this as large as possible? So the prefix is going to be like, to calculate the prefix of some range, it's like CS at end minus CS at start, like cumulative sum at start. Talked about this earlier, but it's going to be like this range minus this range here. So basically what we want to figure out is, we know this cumulative sum at the start, we can just calculate that at the beginning. Then for the cumulative sum at the end, we just want the biggest one. So we can use an RMQ to find what the biggest in this range is. You can also use just a min q if you don't want the log factor from memory. And the min q would give you, or the max q, you'd use a max q, excuse me. But the max q would give you what's the biggest thing in this range of the correct size. And then you can like move it over by 1, and then also what's the biggest thing in this range of the correct size. And that would give you the candidate for this. So that's my understanding of how to solve it. If that's not correct, I'd be pretty surprised. Like if that isn't the correct solution idea. But at the same time, I don't know why my code is wrong. And then for problem G, I didn't get time to do it in contest, so I obviously can't explain the solution. And I guess you'll have to read the editorial for that one. But yeah, anyway, I thought it was an interesting contest. I wasn't a fan of digit descent DP problems, but that's just me. And I hope you enjoyed the contest as well. I think there's a Div 3 coming up on Sunday, so I guess I'll probably speedrun that. But yeah, we'll see. Hope you enjoyed the contest, and hope your rating went up if it was rated for you. Goodbye.